In this video, we'll talk about the properties of sound wave. Now, there are two kinds of mechanical waves. The first one is the transverse wave. Transverse wave. Okay. Now, in this kind of wave, the particle motion is perpendicular to the propagation direction. So let's say here's one particle and it's doing oscillation, up and down oscillation, but the wave is propagating along this direction. So that's the speed of wave, and the direction here is perpendicular to the oscillation direction. Now, one example is the string wave. A wave that rides a string, and you can see the wave shape like this along a string, and then the propagation direction is this way. Okay, and the wave function that we wrote down last time refers to the displacement of each particle along the string. Let's say here, this particle at position X, okay, and at this instant it has position Y. So Y represents the displacement from the equilibrium position. And the horizontal line I drew here is the equilibrium position for each particle. When they're not oscillating, they're sitting right along this line. Now, the second type of mechanical wave is called longitudinal wave. And in this kind of wave, particles' oscillation direction is parallel to the propagation direction. So here the particle, let's say this particle here, is oscillating along this horizontal direction, and the wave propagation is also along this direction. They're parallel. And one example of that is the subject for today, sound wave. Okay. Now, if I draw a similar diagram like this one, then it's hard. You cannot actually draw such a figure here. You cannot see that shape, but what you can see here is the particle's position changing. So now let's say without sound wave, air particles, they're equally spaced, they're uniform. And these black dots right now represent the equilibrium position for each particle. These are all equilibrium positions. But you notice that it's different from the transverse wave. A transverse wave, you can say the equilibrium position for all particles are at the same level, essentially at the same value. But now you have different positions for the particles, and their equilibrium positions are fixed to their position along each equilibrium position, equally spaced equilibrium position. So now if there's a wave propagate along the air, a sound wave, then these particles, they're going to move away from their equilibrium position. So let's say at this instant maybe it's here for the first particle, and second particle perhaps is here, a bit smaller away from the equilibrium position, and the third one even smaller, and the fourth one maybe is right at still at the equilibrium position, and then the next one maybe the particle move to the left side, and the next one to further away from the equilibrium position to the left side. Okay, so if you measure the displacement for all these particles away from the equilibrium position, then we can still use y. So here, this displacement is y1 for the first particle. Now second particle is a little bit shorter, so that's y2, and it points to the right. Now y3 is even smaller. Now y4 is actually 0. So let me point this out. Now the next one, the displacement is to the left side. So at y5, which is negative, and previously we have all these positive displacements. Okay, and y6 get even more negative. That's y6. Okay, so that is very similar to the case in the transverse wave. So for example, this particle here, the displacement is positive, and then becomes even more positive here, and then less positive, and then now becomes negative, more negative, and less negative, and then also, of course, equilibrium position here. These particles now moving. So we have exactly the same situation. It's just that for each particle, now you need to use different equilibrium positions to measure that displacement. Y here still represent the displacement. Displacement from the equilibrium position. Okay. All right. So that's the concept of longitudinal wave, and again, the sound wave is the wave is the subject for today's lecture, and we can still write down y as a function of position and time. Okay, and if the wave source is oscillating with harmonic wave, simple harmonic wave motion, then we should have similar equation that we had earlier for other string waves. So it's given by a sine kx plus or minus omega t, depending on a right moving wave or left moving wave, plus phi naught. Okay, similar kind of equation. And then you can do the same thing, like if you take the derivative here, then you get Vy, the particles velocity along this oscillation direction, and that is given by dy dt for each position y. Then you get plus minus omega times a cosine kx plus minus omega t plus phi naught. Now ay is the Vy derivative with respect to time, and then we get omega square, negative omega square, and then times a times sine. The same equation here. Now that's the derivative with respect to time. Okay. Now what could be the meaning of the derivative with respect to the position? With respect to this position. Okay. Now it turns out that the that derivative will give you either a force or pressure in the case of sound wave, because of the pressure here. And the wave equation is still like before. So we have the second derivative of the displacement with respect to x squared, that equals a coefficient times, which is 1 over v squared, times the second derivative of y with respect to time. So that's the wave equation for any traveling wave, and now in particular here, the sound wave. Then we have a different expression for this v here. Okay, now v is given by, the speed of sound is given by square root b over rho, and b here is called the bulk modulus. So it's a coefficient related to the pressure in the air, and rho here is the density. Okay, now here the density is a three-dimensional density, so it's given by, let's say we have a certain value of air, let's say m here with mass m, and we know its volume is v, capital V here, then rho is defined this way. So it's a three-dimensional density. All right, so that's the speed of sound relation to the air property, the materials property. And the speed of sound is usually 343 meters per second. Usually the question will give you these numbers here, and that actually has a condition. So the air speed equals this value only around 20 degrees Celsius, around room temperature. And that's like the most used value for the speed of sound, because we usually speak at the room temperature. Now, it does have a temperature dependence. So here's the equation that people derived. Speed of sound equals T in unit of Celsius plus 273 divided by 273 and then times 331 meters per second. Okay, so it's like an equation people derived just for the air speed, the sound speed in the air. And if you plug in 20 degrees here, you get 343, the value we use for some calculations. Okay, that's the speed for sound propagation in the air. Now it turns out that when air particles doing oscillation in the air, it can also cause pressure change. And the reason for that is because of the density of the air changes. The reason we have here is because of the density change at each point. So that's a kind of a modulation of the density throughout the sound propagation. And the higher density point will give you a higher pressure, and lower density regions will give you a lower pressure. And of course, if there's no sound propagating in the air, then the pressure is a constant because the density is a constant. So let's first discuss this situation. So let's say there's no sound wave. Now we have a uniform density, air particles density throughout the region, and then that will give us some pressure. Let's call it P naught, which is the you can say average pressure of air. And this average pressure is like the equilibrium value. And all other modulations, so let's say that's sound wave propagation in the air, okay? If there's such a propagation, then at some places, the pressure is greater than P naught, okay? and some other places pressure is less than P naught. And of course, there are regions where these pressures are equal. So that's why we want to do we want to calculate the difference between them. Because remember in the previous diagram, the reason we have this y here in the expression here, y is with respect to the equilibrium position. And sometimes the displacement is to the right, sometimes to the left. So that's why we have positive value, we have negative values. So now if the pressure is defined in the same way, we say, how about P minus P naught with respect to some equilibrium value, then we have this P called pressure change. And pressure change should satisfy the equation that we had for the wave propagation, either sine function or cosine function. And this pressure change should be proportional to the wave propagation function. And it turns out to be exactly this case. So if you take a derivative of the y is the displacement of the air particle with respect to the position, as I mentioned earlier, this derivative here, not with respect to time, but with respect to the position, give us something related to the pressure. And it turns out that if I multiply B, the bulk modulus, and add a negative sign, I will get this delta P. I'll get this pressure change. And just like in the case of the displacement y, we don't call that delta y. We just call it y because we set the origin right at the equilibrium position. Then we have delta y equals y. Now we do the same thing. If we set the, you can imagine that the origin is set at P equals P naught, the equilibrium value. Then the displacement here away, the pressure change from the equilibrium position, delta y is y. Delta P is P. So that's why we call it P here. And it's also a function of position and time. And if I take that derivative of y with respect to x, then I get, let's recall it y's expression. So y equals a sine kx minus omega t plus minus omega t plus y naught. That's our previous equation, okay? So let's take a derivative of that. Let's see. Partial y, partial x give us an additional k factor, bka, and then cosine function, kx plus minus omega t plus y naught. Okay. Now let's do something here. Let's absorb this negative sign into the cosine function. And then let's also change the cosine to a sine function. Now if I do that, then I find this expression. So bka becomes a sine function, cosine becomes a sine function, kx minus pi over 2. Okay, so if I absorb that negative sign, then I get some additional factor here. Okay, and let's call this thing here phi naught. Then we have this expression. So the pressure as a function of position and time is given by pka sine kx plus minus omega t plus phi naught. All right. Again, remember this P here is the pressure change with respect to P naught. And in the region, just some definition here. In the region where density becomes higher, So imagine that two particles, they're moving to each other, and then this region becomes higher density region. So we have higher density region here, and that would represent positive P, right? So higher pressure means that the pressure value is greater than the equilibrium value, and then that is the region called compression. Now, if particles move away from each other, let's say some region have this, then this region becomes lower density region. And the pressure there would be less than the equilibrium value, so P is negative. And that kind of region is called the rarefaction. Okay, here are just some definitions of the names. Now let's talk about the one phenomena special to the sound wave. It's the Doppler effect. So Doppler effect is the change of the sound frequency due to the speed of the sound source or listener, or the sound receiver or listener, or media velocity. We're going to talk about this one the last, because we're going to talk about the for these two, we're going to think about still air case. So it means that there's no, in this case, there's no media speed or velocity. So the air is not moving, wind is not blowing, and that's our case here, still air. And then later on we'll add the media velocity, okay, the effect of that. All right, so that's before I talk about that, let's first think about how to draw a sound wave. Because in previous videos we talk about one-dimensional wave, such as string wave, and it's very easy to draw that because it's just one dimension, and then let's recall it. So we just draw like a sine function, and then that's it, right? So that's the wave shape along this x direction. But for a sound wave or other three-dimensional wave, we actually need to draw three dimensions. So you can have a wave source here, and it emits a sound wave in any directions, right? So let's say, as usual, the right side we have this x-axis here. Then the sound wave look like, if I just look along this direction, it will look like this. So here I'm drawing the position y away from the equilibrium position for each particle, and it's given by this kind of shape. Now the sound wave again propagates along any direction. So now if I think about this direction, another x-axis, let's call this x1. Actually, this one's x1, and let's call it x2 along that direction. Then it's kind of like we rotate this x1 by 90-degree angle, and then you get this x2. So now here's the, I'll try to draw a similar diagram like this, okay? And then if I want to further think about this direction to the left side, now I will rotate this again by another 90-degree angle. And then further away this direction, I'll have this oscillation. And then if we draw every one-dimensional wave along any direction, then they all overlap, and it's hard to see the property of the sound wave this way. So that's why we're thinking about just look at some special points along the wave propagation, and we're going to just look at all the crests of the wave. Okay, by crest we mean the highest displacement position, such as this point, that point, this point, and this point. Okay, so all these represent the largest displacement from the equilibrium position, and we call that crests. And another position, the troughs. So the definition here is that crest is the largest, it has the largest displacement, positive displacement from the equilibrium. And of course, there's these troughs of the wave, which means largest negative displacement from the equilibrium. So that would correspond to this point, that point, that point, and that point. Okay. So it turns out we just need to think about all these special points, and then we can already figure out the wave property. And especially we just use the crest. Okay, and the collection of the same set of crests, meaning the distance to the wave source are the same for all these crests, give us wave front. So if I connect all these points that have equal distance to the origin, then I get, for example, these points. And it's not like a two-dimensional circle here. You can imagine it, you use radius r, and then you draw a sphere around this center here, and then you get all these points along the surface of this sphere that give us the same property. They're all crests, and this is called the wave front. Let's call this wave front number 1. Okay, now we have another set of crests. That's this and this point and this point, and then for this wave, that's this point. Okay, and if I connect them all, let me try to do that. It's too big now. Then we get to the second wavefront. Okay, so let's call this wavefront number 2. Okay, now once we do that, the distance, so let's say I draw a radial line along this dashed line, and the distance along the radial, okay, between the two wavefronts is called the wavelength lambda. Okay, because if you look at the one-dimensional diagram, this wave in particular, you have the crest distance given by the wavelength, right? So that's the wavelength lambda along this way, and that's why the distance between the two successive wavefronts is wavelength. Okay, and it's the distance between two successive wave fronts. So that's why in the future, when we draw either 2D or 3-dimensional traveling waves, we're going to just draw their crest, just draw their wavefronts. So here's an example. Let's say the wave source is here, and then we draw the first circle around the center, and then second circle, and then and so on. You have a third circle, and all this distance between the successive two wavefronts is lambda. Okay, so that's important because we need to use this kind of diagram to talk about the Doppler effect. Okay, so now let's talk about the Doppler effect. So now again, let's think about the sound source is stationary. So we're thinking about let's say there's a speaker making sound, and speaker is not moving. Okay, so here's the source, and then we can draw, like in the previous pictures, a series of concentric circles to represent these wavefronts, like this. And then the next one would be, so let's say right now there's a crest emerging here, okay? Then this distance is lambda. Now if I draw another lambda away from the center, then okay, this set of concentric circles, it's another lambda. Okay. Now since we know the speed of sound, let's call this Vs. Okay, Vs represent speed of sound in air. Then Vs equals lambda times f. So if we're given, let's say, the frequency of the source, let's call this Fs, frequency of the source, then according to speed of sound, we can calculate the wavelength of that wave source in air, in the still air, meaning air is not moving. We talked about that earlier. we can do the calculation. But now the question is, what happens if the source is moving? And let's give this source a speed. Let's call it Vs here. Okay, so now it's confusing. So let me get rid of this previous Vs here, and let's just say that V is the speed of sound in air, and that's this V here. Now I use S here to represent the source. So this Vs here represent the source velocity, wave source velocity, or wave source speed. All right, so think about this picture here. How do I change that if the source is moving? So we know it takes capital T time. Let's say there's a crest emerging from here, and it takes capital T time to travel to this location. At instant capital T, the period of the sound wave, then the wave is propagated to here. After another t, let's say 2t, then it propagates to this new position here. Okay, we can use that. So let's think about, let's say, at instant t equals 0 second, there's a crest emerging from the source. And then after capital T time, we know it's going to be here. Just like before, it's going to propagate to this position here at t, right? However, the source is moving in this direction with velocity Vs. So after capital T, it moves distance Vs times t to these new positions. Let me use the red dot here. Now the red dot represents the wave source position at capital T instant. And at this instant, we know there should be another crest emerging, another wave front coming out from the wave source. So that will give us the new diagram that we can draw. So the new crest will be forming, new wave front is coming out from the source in this way. And then the first wave front that we emit at t equals 0 second now is here. At instant capital T is here. Okay, so now the new wavelength, let me call this wavelength lambda front, meaning it's in front of the wave source, is less than the previous wavelength, this wavelength, lambda. Okay, so it's going to be, this lambda front is going to be less than the lambda that we calculated earlier. And you can imagine that the wave source is like squeezing the wave front in front of the, wave front in front of the wave source. And for the wave propagating to the left side, so at t equals 0 second, when the wave source is here, it emits a wave, right? And after capital T time, it's going to propagate to this position, just like before. It's going to propagate to here. Yeah, that's the first wave front that we emitted, the wave source emitted. It's at least it's at least position here. Now the second wave front emitted to the left side, it comes from this new position of the wave source, and it should emit a wave front that look like this. So that's why there's a distance. This distance here give us the wavelength behind behind the wave source. And then this wavelength is greater than the lambda that we had for the if the source is not moving. Okay. Now, how to calculate these two values? How to calculate lambda front and lambda behind? So we notice that the lambda front is given by the original lambda subtracting the source movement along this direction in time capital T. Okay, so we should do lambda minus Vs times T, and that should give us lambda front. And lambda behind is the opposite. It's lambda plus Vs times T. Okay. Now lambda, remember, is given by the V here over frequency, right? Frequency of the source. And V over frequency of the source is V times T. 1 over the frequency of the source gives us the period T, right? So that's why we have V minus Vs times T. Okay. Or you can say, if I want to use the frequency of the source as the variable here to do calculation, then I should divide it by Fs. Okay, so 1 over Fs is T, the source frequency or the source period. Now, if you do the same thing for the lambda behind, then we should get V plus Vs over Fs. Okay, so that's the wavelength change. Due to a moving wave source. Okay, so that include the effect of the moving source. Okay, so let's introduce the listener to the picture. Now let's introduce some notation here. Like before, we said that V is speed of sound in air, and let's say Vs here represent speed of the source or source velocity. Actually, let's call it the source speed. And VL here represent listener speed. Alright, so think about first case. Let's say the source is now moving. Here's the source, here's the listener. So source is not moving, listener is not moving. Both are stationary. Now the speed of sound that propagates will be the same as the V here. So the frequency the listener hears is V over lambda. The uniform wavelength when the source is not moving is lambda. So that's V over lambda. And that gives us the source frequency. Okay. But again, let's first recall the definition of the listener frequency. It's the number of wavefronts received by the listener per second. And the frequency here will be equal to the source frequency. Now, second situation, if source speed is non-zero, so let's say source moving this way, and listener has no speed. Now, the frequency listener hears is, so first we know after the wavefront leaves the source, the wavefront will propagate with velocity v here, with the sound speed. And the listener is in front of the source, so it's going to, the listener here is going to hear the compressed wavelength. So it's lambda flat. So that's why we have V over V minus Vs over Fs will give us this expression. Now, what happens if the source is not moving, but the listener is moving? Moving toward the source. Now, here is the frequency listener hears. Now, after the wavefront leaves the source, it's going to propagate with speed v. But because the listener is moving toward the source, so the relative velocity of the wavefront with respect to listener increases by this amount. And then the wavelength still in front of the source, so still have that, but now we have V plus VL, V minus Vs times Fs as the frequency listener hears. Now, what happens if the previously here, the lambda is the regular lambda because the source is not moving, right? So we have the lambda here is equal to the regular V over Fs, and let's get rid of this. And this will give us V plus VL over V, and then times Fs. So now what happens if both of them are moving? So that's listener, let's source, that's listener, and they both moving toward each other. Then the listener hears the frequency, the relative velocity becomes greater, and the lambda here now is lambda flat, and lambda flat is V minus Vs over Fs. Then we have V plus VL, V minus Vs times Fs as the frequency listener hears. Okay. Now we can actually do the same thing. So if the source is moving this way and listener is also moving in some direction, let's say this way, then it turns out the frequency equals. Now still the relative velocity of wave propagation with respect to a listener is increased by this expression. But now the lambda is lambda behind, because now the source is moving away from listener. And then we should have V plus Vs here over Fs to represent the lambda behind. V plus VL still true. So we have this expression for the frequency the listener hears. Okay, so all these situations can actually be summarized by this equation. So the frequency listener hears is equal to V plus minus V listener, V plus minus V source times Fs. Okay, now when I say plus or minus sign means that we need to determine, or we need to pick a sign here when we do the calculation. And here's how you pick the sign. Now let's say that's the source and that's the listener. Okay, now I'm going to draw a direction as reference direction. The reference direction is pointing from listener to source. And this direction is defined as positive direction. Again, it's from listener to the source. Okay, this direction is positive. So let's check some other velocity direction. So let's say the source is moving. Suppose the source is moving this way. Okay, and listener is moving this way. Then the source is in the opposite direction to the positive direction that we defined earlier. So we need to pick negative sign. And for Vs, and for the VL here, because it's in the same direction as the positive direction, so we need to pick the positive side. So the formula that we should have to calculate the listener frequency should be V plus VL, V minus Vs times Fs. And that is this equation here. And that's the situation we were talking about. So now let's see if the source is moving this way, listener is moving this way. Okay, now both are positive according to the reference direction, the positive direction, which is from listener to the source. They're in the same direction. So that's why the listener should hear the frequency V plus VL, V plus Vs times Fs. And that's exactly the equation here. Okay, so that's why let's circle this again. So that equation summarizes the Doppler effect due to the source velocity and the listener velocity. Okay, and the positive direction again points from listener to source. Finally, let's discuss the effect of air speed or wind on the Doppler effect. Let's simplify the situation. So let's say the source is not moving. So here's Vs, the source speed is 0, and then listener is also not moving. So look at this case first. So if the wind is blowing, and let's call that air speed, Va. So Va is non-zero. That's for the wind speed. So now if the source here emit a crest, let's say at t equals 0 seconds. Now after one period, capital T, it moves here. This crest here move to this new position. Suppose there's no wind blowing. Okay, so the first case here is VA equals 0. So now think about VA non-zero if there's a wind blowing. So again at t equals 0 second, there's a crest, wavefront emerge from the wave source. And then because the air media here is flowing this way, let's say VA is this way, okay? This way. Then it will carry this wavefront further compared to the previous positions here without the air speed. But now with the air speed, it will carry this further away to this position at t equals capital T, and again previously is t equals 0 second. And then at this instant, the source will emit another wavefront right here. So that means that compared to the previous wavelength lambda of the wave, the lambda here increases. Let me call it lambda A, okay, due to the speed of the air. So lambda A is going to be greater than lambda. So that's an increase of wavelengths. So now that wavelength, right, equals the speed of sound plus the air speed, and then multiply capital T here. That gives us the new wavelength. And previously, without the air moving, we have lambda equals just v times t. Okay, so again, v is the speed of sound in a still air. So the effect here is of the wind blowing is the increase of the speed of sound from v here to v plus va. Okay, so let's summarize the effect here. So the effect is that the speed of sound increases from v to v plus va. Okay. Now, if I look at the other direction, let's say if the source is emitting a crest to the left in this direction at t equals 0 second. Okay. Now, without VA, VA is still this way. Okay. Without VA, it would be here. That's when VA equals 0. But with VA, because the media is blown away in this direction, opposite to the sound propagation, and the speed of sound will be effectively reduced to this position here. So the wavefront can only arrive here at t equals capital T, instead of further away the dashed line without the wind speed. So here is wind speed non-zero. So on the other side, the wavelength is effectively reduced. So lambda A here is V minus VA times T. Okay, and both T's are equal, right? Because we don't change the frequency of the source emitting the sound wave. So at every t second, you emit one crest or one wavefront, and that cannot be changed. So that's why the effect of the wave propagation on the other side is that the speed of sound decreases from V to V minus VA. Okay. Okay, now to summarize both cases, we need to change the speed of sound from V to either V plus VA or V minus VA. So that's our conclusion here. V speed of sound change to V plus minus VA. Okay, and depending on the side of the listener with respect to the sound, with respect to sound source, and also the wind speed direction, we need to take either positive or negative sign. So finally, the Doppler effect. Listener hears, let's call this V plus minus VA, the new sound speed. and then plus or minus V listener divided by V plus minus VA plus minus V source, and then multiply F source frequency. So that gives us the effect of source moving, listener moving, and also the wind blowing. So three velocity effect, they summarized in this equation here. Okay, so that's all for this video. Thanks for watching. In this video, we will continue our discussion of the standing waves. And remember previously we talked about the string system, right? So that's the string instruments. And we know how to count the standing wave orders. So now today, let's talk about pipe instruments. And the system looked like this. So that's a pipe, and usually there's air inside. And then we're going to talk about different situations. Okay, so that's how to count standing waves in a pipe instrument. And for the pipe instrument, we can have different kind of situations. Let's talk first about the open pipe. Okay, now the picture looked like this. So both ends are open to the air, to the outside air. Okay, and the length of the pipe is L. Okay, and then just like before, we could have two kinds of situation here. We can use the displacement yxt of these air particles, and then we could write down y1 plus y2 of the two sound waves inside the pipe. They superimpose, and then we think about the boundary condition here. Okay, the boundary condition. So the boundary condition here is that before we talk about this, actually one more thing here. So remember the for sound wave, there are two kind of wave equation we can write down. One is using the displacement. That's the yxt that we talked about earlier. And the other wave equation we can write down is using the pressure, where we have pressure as function of position and time. Two descriptions. So now the boundary condition is very important. If the pipe both ends are open, that means that the air inside is connected to the air outside through this boundary, and at the boundary they should be continuous in the pressure. So for open boundary, the pressure inside the pipe equals the pressure outside. And because the pressure outside is a constant value, that means that they must be zero here. So the pressure inside at the boundary should be equal to zero here. That means that it's node of pressure. Now remember, the relation between P and Y is that P is given by negative B partial Y partial X. Okay. Now by doing that, if y is a cosine function, then it turns into a sine function for p. If y is a sine function, then it turns into a cosine function for p. But in either case, if p equals 0 here for a node, then y must be 1, which must be an antinode. It's an antinode of displacement. So that's the open boundary condition. From there, we can say this n is p pressure node or y antinode. Okay, so now the same can be said about the other end, which is also open, which means that it's also p node or y antinode. And then later on, we'll talk about using these two boundary conditions. We can draw different orders of standing wave inside a pipe. Okay, but that's for later. Right now, let's think about closed boundary. What do we mean by closed boundary, and what's the implication for the pressure and displacement? Okay, now an example look like this. So let's say we put a cap on both ends, then that's closed, and that's closed. Now for closed pipe, we know the sound wave is a longitudinal wave, so the particles will try to like vibrate along this direction, and their propagation direction is also this way. Okay, so that's the longitudinal wave. But at the boundary, think about a boundary particle. A particle here cannot vibrate because it's blocked. The particle here will just stick to the wall, to the cap, without doing any motion. So that's why it's the closed boundary here is the node of displacement, which again, according to this relation between pressure and displacement, is the antinode of pressure. Okay, so that's an important condition we can use later on to talk about the standing wave orders. Okay, so let's start right away with the open pipe. Now here's the diagram. Both ends are open. And we also want to build a coordinate system so that origin O is sitting on one end, and the other end here is at L. That's the length of the pipe. Okay. So now the first order standing wave is given by remember both ends are open, so it should be Y antinode at both ends. So I still pick Y, the displacement, to discuss the standing wave. But before I do that, let's draw a diagram. So now if I have a sine function, then I have a shape that looks like this. Okay, so you want to have a antinode, so you want to pick this point here, right, to fit into one end, and the other end would be the other end, the other antinode, and that means that our origin O should be here, the left end of the pipe should be here, and the other end, the right end, must be it could be here actually, or there. So the first possibility is here. That's the right end, number one possibility. And number two, the second order would be here. Right end is fit here. Okay. Now this distance is lambda over 2, and the second distance is lambda. Okay, the total wavelength. So that's why we have the first order standing wave, where we have length of the pipe equals lambda 1 over 2, or lambda 1 is 2L. Okay, and then let's say we know the speed of sound is 340 meters per second at room temperature, and that equals lambda n times Fn as before. Then we have F1 equals V over lambda 1 equals V over 2L. That's the, again, fundamental mode. Now second order, L equals, now we have lambda here, a total lambda, so it's lambda 2, or you can say lambda 2 is L, F2 equals V over L. And nth order, L equals n times lambda n over 2, or lambda n equals 2L over n. Frequency is n times V over 2L, n times F1. So F1 equals V over 2L is the fundamental frequency. So all these orders, the length of the pipe satisfies exactly the same equation as in a string case. Now how about let's think about the same problem but with pressure. Instead of displacement, think about pressure here. So that's the pressure node, and also pressure node on the right side. So now if I think about the sine function again, the left end should fit here because that's a node for the pressure. And then the other end here should be, could be here, right? This first possibility is here, and second possibility, third possibility. So that's the first order, second order, third order. And that give us the relation between the length of the pipe. Let's say n equals 1, first order. So L equals lambda 1 over 2. Then we get lambda 1 equals 2L. Now second order, L equals 2 times lambda 2 over 2. So lambda 2 equals L. Now nth order, L equals n times lambda n over 2. So lambda n equals n times, sorry, two L over n, okay? And then correspondingly Fn equals n times V over 2L. So that look exactly the same as the previous nth order. So that doesn't make a difference. So you can use either the displacement or the pressure to talk about the standing waves. They should give you the same equations. All right, so let's mention the closed pipe quickly, okay? Now here's the pipe, the length is L, both ends are closed, and that means that their Y node on both ends, or you can say both ends are pressure antinode. Now according to that, you can do the same discussion as we did here, and then it turns out the equation looks exactly the same. So for the nth order standing wave, we have lambda n equals 2L over n, and frequency Fn equals n times V over 2L. Okay. All right, so let's talk about open closed pipe. Okay, now this should make some difference because here's the picture. So one end of the pipe is closed and the other end is open. Okay, so now that means that the left end here is displacement node, and the right end here is displacement anti-node. Or you can say the left end here is pressure anti-node, and the right end is pressure node. Okay, and you can use either one. You can use pressure or displacement. So let me pick the displacement here, and let's look at this sine function. Now I can fit to the left end. Let's say I'm thinking about y here. Okay, the left end is the y node, so that means that that's this one is okay. So that's left end, and right end should be displacement anti-node. So that should be this one, right? Or you can say that one, or the next one will be here. So the first order should give us the length of the pipe. So first order length of the pipe equals 1/4 of the wavelength, lambda 1. So lambda 1 is 4L. Okay, or you can say frequency F1 is V over 4L. Now second order standing wave is here, right? So we have the length of the pipe equals so that's like 3/4 of lambda 2. Okay, and then that gives us the lambda 2 here equals 4L over 3, and the frequency is 3 times V over 4L. Now the next order is here. Third order, L equals 5/4 lambda 3. So lambda 3 equals 4L over 5, and frequency equals 5 V over 4L. Okay, so now we can generalize the situation to, let's say, lambda nth order equals 4L over so I'm going to define n here as 1, 2, 3, etc. So to get to the first order, I need to do this n here should be that's like 1 here, right? So it's actually it's 2n plus 1. So I'm going to say n start from 0. And then for the first order, that refers to n equals 0. And then when I plug in 0 in this expression, I get 1. So I have this one here. So that's why it's 2n plus 1. And for the second order, I have n equals 1. And when I plug in here, I get 3. So that's why I have 3 here. For the third one, n equals 2, so I get 5 here. So that's why the lambda n here is representing n equals 0, 1, 2, 3, etc. And we have 4L over 2n plus 1. And the frequency Fn is 2n plus 1 times V over 4L. Okay, so again, n is 0, 1, 2, etc. Alright, so let's give you an example of how to count the standing waves in open-closed pipe. Okay, so now lastly, I want to talk about the energy. in a wave. So now let's see, here is the wave source. And let's say wave source has power P, okay? So it means that it emit the amount of P energy per second. Emits energy P per second. Okay, so that's the definition of power. And then you will emit in all directions. And let's think about the isotropic media. Means that in any direction, the propagation of the energy is uniformly. So that's why we can say, suppose there's a spherical surface that's radius r, and then we can think about the energy distribution on such a surface. So we're going to calculate energy per unit area. We call it I. Is total energy P divided by the total area of the spherical surface, which is 4 pi r squared. And that is the energy distribution we call it intensity. So it's power per unit area. It's defined this way. Now with this intensity, we can also apply it to the sound wave. And people try to measure the sound wave intensity, and then they use another unit called decibel. Decibels, that's like a unit for intensity. So how to define this? Because the hearing of human being, the intensity that human being can hear has a really large range. So it starts from the lowest intensity that people can hear is 1 times 10 to the negative 12 watt per square meters. So by the way, the unit here for intensity is watt per square meters. Okay, so that's the hearing threshold for human being. Human being can hear this small intensity and go up to some very large intensity, like order 1. So that's the huge order of magnitude that we need to cover. So that's why watt per square meter is not a proper unit. So decibel here is a proper unit. And let's define this decibel. Decibel is given by this formula. So that's a 10 decibel constant times a log function using 10 as the base. And we have intensity I over I naught. Okay, so every intensity need to be compared with the hearing threshold of human being. And that ratio need to be input into the log function, which is 10 as the base. And then we get the decibel. So let's say some example. So let's say we're thinking about, let's say 10 decibel. And think about what is that, okay? So if beta equals 10, then the intensity satisfies this equation. That means that I over I naught equals 10, right? So So I equals 10 times I naught. So that gives us 10 to the negative 11 watt per square meters. Okay. Now another example, let's say beta equals, let's say 100 decibel. And what is that? So let's see, we have 100 here for the left side. Then we have I over I naught equals 10 to the 10th. So the intensity is 10 to the 10th times 10 to the negative 12. So that's 10 to the negative 2 watt per square meters. Okay, so that's why the range of the intensity is very large for using unit watt per square meter. So that's why it's not as convenient as the decibel unit, where we have just a small range, some regular number that you can say. Okay, so that's all for this video. Thanks for watching.